15.4 Green's Theorem, Part 3. Let's find the outward flux of this vector field across the boundary of the annulus. The annulus is not simply connected, so we define our curve to be the piecewise smooth curve shown. The links L sub 1 and L sub 2 along the x-axis are parallel and are traversed in opposite directions. Therefore, the contributions to the line integral cancel on our links. Because of the cancellation, we can take our curve to be the curve that runs counterclockwise on the outer boundary and clockwise on the inner boundary. Note the direction of the outward normal vectors. So we're first going to find the two-dimensional divergence of the vector field. Then by Green's theorem, outward flux is the double integral of y squared plus x squared over the annulus. I'm going to describe the annulus in terms of polar coordinates because it's pretty easy to switch the double integral into polar coordinates. So switching it to polar coordinates and integrating, I get 15 pi over 2, a positive value. The figure shows why the flux across C is positive. Because the field increases in magnitude at greater distances from the origin, the outward flux across the outer boundary is greater than the inward flux across the inner boundary. Hence, the net outward flux across the curve is positive. A useful consequence of Green's theorem arises with this vector field. The curl of this vector field is equal to 1. And so Green's theorem gives us, it tells us that the line integral of x dy over the curve is equal to the area enclosed by the curve. Stick with me a little bit longer on this. Likewise, if we use a different vector field, we can get another formula which equates the line integral of y dx over a curve to the negative of the area enclosed by the curve. Now, we're going to put these two pieces of information together. Take the first equation we found, subtract the second equation, and divide by 2, and we get this useful formula that arises from Green's theorem. Under the conditions of Green's theorem, the area of a region R enclosed by a curve can be found using this formula. Now, we need to see this in action for this to make any sense to you. Let's use this result to find the area of this ellipse. We're going to first, what we first need to do, if we're going to do a line integral, is we need to parameterize our ellipse. So have x be a cosine t and have y be b cosine t. That way we can find the line integral. And we use this parameterization to find the line integral. All right, so we need to find x dy minus y dx. So what is dx? What is dy? Using this parameterization, dx is negative a sine t dt, and dy is b cosine t dt. All right, now find x dy minus y dx. When the dust settles, it takes a little bit of calculation. Also, you'll have to use the Pythagorean theorem, cosine squared plus sine squared equals 1. When the dust settles, you'll get AB dt. All right, so we're ready to find the line integral. With this parameterization, we're just finding the integral of 1/2 of our AB dt with t running between 0 and 2 pi. That's a pretty easy integral. And we get AB times pi. So using Green's theorem, we found that the area of the ellipse is AB pi square units. And keep in mind that if A and B are equal, we have a circle, and that's consistent with pi r squared. All right, consider a two-dimensional vector field where f and g have continuous first partial derivatives on a region. A stream function for the vector field is a function psi that satisfies psi partial y equals f and psi partial x equals negative g. If the function psi exists for the vector field, then the divergence is psi yx minus psi xy. Since the partial derivatives of f and g are continuous, the second derivatives of psi must also be continuous. So, the second derivatives have to be equal. That means the divergence of f is 0. Now, a divergence of 0 means what? That's correct. It means source-free. So the existence of a stream function guarantees that the vector field has 0 divergence, or equivalently, is source-free. The converse is also true on simply connected regions. Source-free implies the existence of psi. The level curves of a stream function psi are called stream lines. The vector field f is everywhere tangent to the streamlines, which means that the graph of the streamlines show the flow of the vector field. Just as circulation integrals of a conservative vector field are path independent, flux integrals of a source-free field are also path independent. All right, time for a review. So wrap up. The following statements are equivalent to saying that a vector field is conservative on a region in two-dimensional space. Now, the backwards E means there exists. All right, so the following statements are all equivalent to saying that the vector field is conservative. There exists a scalar function phi such that f is the gradient of phi. There exists a scalar function phi such that the line integral is equal to phi evaluated at B minus phi evaluated at A. So that's that path independence. For a smooth closed curve, the line integral or circulation is equal to 0. The vector field is irrotational, meaning the two-dimensional curl is 0. Now let's go to source-free. The following statements are equivalent to saying a vector field is source-free. The divergence is 0. There exists a stream function phi such that f is phi partial y and g is negative phi partial x. The vector field is everywhere tangent to the level curves of phi, and the flux integrals are path independent. Some more summary. The next set of slides summarizes properties of a conservative and source-free vector field in two-dimensional fields. I'm sorry, yeah, I mean conservative vector fields or source-free vector fields. We're going to assume that our curve is closed and simple oriented curve with this parameterization. All right, so I'm not going to leave much time for you to look at this, so you're probably going to want to turn off the video to look at this. But and then I have one more slide for you to see. So look at this one. And then look at this one. All right, now what we're going to do next, and it's going to take a couple sections to get there, we're going to lift Green's theorem up to three-dimensional space. If we do that, when we discuss circulation in three-dimensional space, we're going to be talking about Stokes' theorem. And when we talk about flux in three-dimensional space, we're going to talk about divergence theorem. All right, it's going to take us a while to get there because you can see it's 15.7 and 15.8, and right now we're in 15.4. All right, so I will see you again in 15.5. Take care.